let's get started. I'm happy to give this lecture for you guys. I will talk about experiments where some evidence was obtained in the past, say, 3 years of the existence of Majorana Fermions, which I understand you already had covered in the previous lectures, what Majorana Fermions are. It's one of the remarkable manifestations of topological phases in solid state. I will actually talk essentially about two experiments. One that I took part in myself in Delft, which is based on semiconductor nanowires, and another one by a group at Princeton, Caltech. A student from Princeton is now a professor at Caltech, Stevan Sergey, who did it with magnetic atoms and an STM tip. I will introduce Kitaev model to you, which is the model that generates Majorana Fermions, but from my perspective. So not a rigorous theoretical perspective, but a qualitative perspective. I hope it will be useful for you. Then I will show you how Kitaev model maps onto a real physical system, which is a semiconductor and a superconductor, and then show you the experiments. Okay. So we start with fermions. Fermions are described by operators of creation and annihilation of fermions. Fermions, like electrons or holes, are well known to all of us, and they occur in free space, right? Flying electrons, positrons, and so on. They also occur in materials in the band structure, quasi-particles, which can be electrons and holes. And in that case, the creation operator is the creation of an electron. The annihilation operator is like a creation of a hole. So these are the standard fermionic operators. And then for Majorana fermions, you have these gamma operators. So what are gamma operators? Well, if we look at the right-hand side here, gamma operators are just responsible for the real and imaginary part of the creation and annihilation operators. So creation and annihilation operators are just some complex number. And if you write it as a real plus imaginary part in this form, then these gamma 1 and gamma 2 are these Majorana fermion operators. Now, you can see from this that both gamma 1 and gamma 2 are real numbers, right, from this formulation. And if you extract gamma 1 and gamma 2 from this, you can express them in terms of C dagger and C of the standard fermionic operators. And you will see that they are an equal superposition of creation and annihilation. And that also means that they are a particle that is also their own antiparticle. So you can write an expression that gamma dagger equal to gamma in two different ways. You can observe that they are real, and that means that gamma dagger must be equal to gamma. Or you can see from this that if you complex conjugate this expression, you will get the same expression back. So this formula is then the definition of a Majorana fermion that we will going to run with. And we can represent them as these half-filled circles, right? And this is a clear notation. It's because they are half creation, half annihilation, half filled, half empty circle for this reason. Now, a historic note that this name Majorana fermions was used for fermionic operators like this by Ettore Majorana going back to 1930s, and in the context of high energy physics, he was trying to solve the Dirac equation, and he found a real solution which satisfies this formula for particles, like, for example, neutrinos. And some people are still running complicated big-scale experiments, try to verify or disprove that neutrinos are Majorana fermions obeying this equation. We are going to talk about quasi-particles which live inside solids, and the quasi-particles are composite. They're made of other particles. Ultimately, they're made of electrons living in a crystal lattice, interacting with atoms, and therefore they're made of fermions. These particles are made of fermions, and so you cannot really have a half of a fermion. So if you somehow designate this particle to be half of a fermion, there should be another half of a fermion somewhere else for conservation reasons, for charge conservation reasons, for particle number conservation reasons. And therefore, Majorana fermions will always come in pairs. There can only be an even number of them if you count everywhere in the universe. Okay? All right. Now, where to look for them in solids? So we need to look for something which has a wave function of a particle plus a wave function of a hole. Here we have a semiconductor. So we have a band structure with a conduction band and a valence band, and in between we have the band gap. And we know that, for example, we can shine a laser light on this, and we can excite one of the electrons up to the conduction band, which will leave behind a hole in the valence band. Now, this particle is called an exciton. So this is a particle called an exciton, and this particle is a particle that combines two of these together because they attract, positive and negative attract, and they bind together. So this is an exciton. But this is not a fermion. Here you have actually two fermions, one electron, one full electron, and one full hole. And so two fermions put together have a spin 1. That's a boson. It's not a fermion at all. So for bosons, we are not interested in them. So they can actually be their own antiparticles. For example, photon is its own antiparticle. That's not so interesting. We are looking for a fermion, which is its own antiparticle. So this does not work. This does not work. And a much better place to look for these is to look inside of superconductors. So not semiconductors, but superconductors. And I cannot go into the full background on superconductors in this 1 hour that we have together. But I can tell you that in superconductors, you have these Cooper pairs, which are also composite bosons. So they are two electrons bound together by phonons, typically. In most superconductors, it's phonons. These Cooper pairs form a condensate, and they make it such that the number of the Cooper pairs is not a conserved quantity. So meaning that in the Bose-Einstein condensate, the number of particles is not a well-defined quantity. And so these electrons condensed into Cooper pairs, they can fluctuate the number of them. And so you can take a hole, add a Cooper pair, which is two charges, and have an electron. And this is actually the same thing. It's the same thing to have a hole plus a Cooper pair as it is to have an electron. And therefore, inside of superconductors, there is this particle-hole symmetry. So it doesn't cost you anything to give one Cooper pair into this process, because the number of Cooper pairs is not well defined. And therefore, there is an equality here, and there is this particle-hole symmetry. Particles and holes are the same. So this is a great place to look for these kind of superpositions of electrons and holes, of creation and annihilation, to find Majorana fermions. It's a natural place to look for these. So in superconductors, particle-hole symmetry can be expressed by this expression. So a creation of a particle with energy E is the same as an annihilation of particle with energy minus E. This is the formula for the particle-hole symmetry, expressing the cartoon that I just gave you in this more rigorous form. So from this formula, we can very clearly see where we need to go to look for Majorana fermions. We need to go to E equal to 0. In this case, for the same energy, we are going to have gamma equal gamma dagger. And we're going to have these Majorana fermions. All right. So this is a particle-hole symmetric spectrum of some a defect in a superconductor. Actually, it's inside, for example, a superconducting vortex. You can have some bound state like in a particle in a box. And this is particle-hole symmetric, meaning that around zero energy, the energy levels are symmetric. There is a level at plus E, there is a level at minus E. So there is a hole level and electron level. These are called Andreev levels, Andreev bound states. However, you can see there is no level at zero, and this is for a very fundamental reason. It's like in any particle in a box problem, right? You never have an energy level at zero energy because of quantum fluctuations, because of 0-point motion. It's like in a harmonic oscillator, for example, right? In a harmonic oscillator, you have these energy levels which are h bar omega n plus 1/2. So for any n, which n must be integer, there is never a zero energy level there. There is always this 1/2 factor, which is due to 0-point motion. And so for the same reason, in a trap for single electrons inside a superconductor, there is not a zero energy level. So Volovic in 1999 figured out that if you make a special semiconductor, which became known as p-wave superconductor, which refers to the symmetry of coupling between the two electrons in a Cooper pair. Again, difficult to go into full details of that in one lecture. But basically, in those kind of materials, which are fairly exotic, actually absolutely exotic, don't occur in nature, you can have an energy level exactly at zero. And the reason for that is that 0-point motion is cancelled by Berry phase. There is some geometric phase for when you go around some defect, like a vortex like this. And if you have p-wave symmetry in this superconductor, this Berry phase exactly cancels the 1/2 factor from 0-point motion and makes an energy level exactly at zero. This creates a pathway to generating these robust, stable Majorana fermions living at this energy level at zero energy. And a couple of years later, Kitaev has proposed this famous model where it is conceptually similar to this, but this p-wave superconductor in Kitaev's model is one-dimensional. So this is for a two-dimensional, three-dimensional material, Volovic's result. And this is a one-dimensional. And in that case, he predicted that Majorana bound states are the end states of this p-wave superconductor. So where a p-wave superconductor ends, you're going to have a Majorana fermion. And notice that there is a second one, so they come as pair. So in this case, for the 3D case, if there is one Majorana here, there must be another defect like this vortex somewhere else where there would be a second such level somewhere else. There must be two of them always. Okay, so here's my cartoon of a Kitaev model, which you probably have it already derived for you, but I think this is a useful picture. I'm going to represent by these blue boxes with two stars, I'm going to represent fermions. Okay, so this is a train of fermions. This is a one-dimensional lattice model where on each lattice side, which is a blue square, you have a fermion. And why does the fermion have two stars in it? That's because we have this formula. Right, so this is just my way of depicting that each fermion is like two Majoranas bound together by this expression. Just a real and imaginary part of a fermionic operator. So I line them up in a chain, and this is a tight binding model, so they coupled. They can hop between the sites, and there's an energy to be on a site. This is what Kitaev model is, except what Kitaev figured out that if you make these boxes p-wave coupled, So not standard superconductor coupled, but P-wave coupled. Then you have to shift these blue frames by half a period. This is what P-wave coupling does. So it takes a Majorana from this side, couples it to the Majorana from this side. These now form a fermion. These form a fermion. These form a fermion. And remember, they used to belong to different real fermions before, different lattice sites. What this leaves is an unpaired, this is what this word refers to, an unpaired Majorana on one end and a second unpaired Majorana on the other end. So we have two unpaired Majorana fermions, and this is what we would like to be after. Of course, a one-dimensional P-wave superconductor simply don't exist in nature. These things do not exist. So this model is therefore called a toy model. First of all, because it's a very simple model, simplified. It's a discrete lattice hopping model. But also because it is purely intellectual. It had no experimental value for the longest time. And by the way, if you had a system where you had two conducting channels, for example, two modes put together, you can see how this is trouble, because that means you have two of such chains, and you have two unpaired Majoranas here, and what can happen is they can, in principle, couple and form a real fermion here, and then there is nothing interesting in this system. So you need to have either a way to prevent them from talking to each other, or you need to have an odd number of these chains, 1, 3, 5, and so on. Okay. All right, so this was a sort of very nice and lived for 10 years on the back burner, developed in a theoretical community. However, at about 2010, two of these papers came out in Physical Review Letters within the same week. And they proposed a realistic pathway of mapping Kitaev's Hamiltonian onto a real physical system, which they proposed to be a semiconductor coupled to a conventional superconductor, right? So what Kitaev said is, if you had a one-dimensional P-wave superconductor, which is not possible, this doesn't exist, you could have Majorana fermions. And these people said, take a standard semiconductor, like our industry uses all the time, take a standard superconductor, like aluminum or niobium, a standard metal that we know a lot about, put them together, and you can create Majorana fermions with using these 4 ingredients. So I'm going to go through these ingredients. One-dimensional wire, right? So this is certainly along the lines of what Kitaev was thinking about. So this is a one-dimensional system, and a one-dimensional system is characterized simply by this dispersion relation here. So momentum versus energy is just a parabola. So electrons living in one-dimensional wire are just living in this parabola. Now a slightly more exotic ingredient is spin-orbit interaction. Spin-orbit interaction, however, is also a very simple thing. In a Hamiltonian, it will be a term that is proportional to some material-specific parameter, then spin cross momentum. So this couples spin and momentum. There is a product of spin and momentum in a Hamiltonian. So for the one-dimensional case, what this does is it takes two spin-degenerate parabolas for spin up and spin down and pulls them apart like this, such that they are no longer degenerate except at one point at k equals 0. This energy difference here is called ESO, spin-orbit energy. And this is by how it characterizes how far the parabolas have been pulled apart. So this lifts spin degeneracy. Why do we need to lift spin degeneracy? It's to prevent us from having two copies of the same system, because in every fermionic system we have spin up and spin down, and if we're going to start creating Majorana fermions there, we're going to have one in the spin up channel, one in the spin down channel. and then we're going to have two of them, and they will form a real fermion. Nothing interesting will happen. So there is always a need to remove the spin degeneracy. So how did Kitaev do it? Well, because he lived in a theoretical toy world, he just said this is a spinless p-wave superconductor. So actually, in his case, he just basically said, oh, there's no spin. So, but in the real world, we have to somehow remove spin. And this is a spin-orbit interaction is one of the ways we're going to do it. Now, superconductivity, I already motivated to you why we need superconductivity. It's to have this particle-hole symmetry, to have this resource to create a level at zero energy where you have equal superpositions of electrons and holes. That's why we need superconductivity. And what superconductivity does is it opens these little gaps. You can see these little gaps at around the Fermi level. So Fermi level is here. It will gap the spectrum. So superconductivity creates a gap whenever a band crosses Fermi level. So these gaps are due to superconductivity. And finally, we need some kind of magnetism. So this is also part of removing spin degeneracy, because here just spin orbit alone doesn't remove spin degeneracy, because if we count the number of bands crossing Fermi level, it's 4. And so 2 bands for spin up, going forward and backwards, and 2 bands for spin down. So spin degeneracy is still here. And what we need is 2 bands. So what magnetism does is it becomes to be at odds with superconductivity. They too fight each other. The ingredient 3 and 4 don't like each other in real systems. The reason for that is very simple. Magnetism wants to align all the spins in the same direction. So all the spins lined up. That's magnetism. Superconductivity pairs all electrons in Cooper pairs. And what that does is making spin singlets. Make spin singlets so electrons counter-align to each other. So if you only have all the electrons triplets, this superconductivity, the standard one, will be destroyed. So what's going to happen if you, for example, have the 3 ingredients here and add the 4th one? You're going to start seeing that the gaps are beginning to close. Superconductivity is being suppressed. Gaps are starting to close.
So in this superconductivity here, P-wave parallel?
This is S-wave. Yeah. So it's a singlet standard superconductivity. This is what's so great about these proposals from 2010 is that we did not need to create a P-wave superconductor. No.
So it doesn't become P-wave superconductivity later to
So, good question. It does not become a P-wave superconductor, but the Hamiltonian of this system can be mapped onto the Hamiltonian of the P-wave superconductor. So, we'd like to call this state a topological superconductor. So, there are technically it's not the same as P-wave, but it's a Hamiltonian that can be connected. I'll show the Hamiltonian in a moment. Let me just finish this qualitative discussion here. So when you start turning on the magnetic field, gaps start to close, and in particular, this gap at zero momentum is the most important one. It just simply closes as you increase magnetic field. And at the point where Zeeman energy is equal to this induced gap, which was induced at zero field, this gap completely closes. Superconductivity is gone because there are single particle states all the way to zero energy. And normally this is the end of the story. So if you just put a standard superconductor like aluminum in the magnetic field and make a Zeeman energy equal to superconducting gap, superconductivity is destroyed. This is called Pauli limit. There are other ways to destroy superconductivity, which actually normally kick in before this one, but this one kicks in this is the ultimate. This is the complete finish of all superconducting things. But in this case, where you put all these ingredients together, you keep ramping up Zeeman energy, and it already becomes larger than this delta. And this gap, after closing, reopens again. So it close, and then it reopens. What in fact happens is gap closes, and then it becomes negative. So you can think of it as the whole band went above the electron band. And superconductivity gets recovered. So it recovers after it's been suppressed by magnetic field. And in this recovered state with a negative gap at k equals 0, we have this topological superconductor, which is equivalent to what Kitaev has predicted for spinless p-wave superconductor. Okay. I will discuss this a little bit more so that you get a better grip on this concept, but if you have questions, please ask. Next thing, I just want to show you a Hamiltonian from one of these 2010 papers. This is the Hamiltonian that they solved, and after they found the solutions for it, the solutions were Majorana particles at the ends of this one-dimensional system. So this is a Hamiltonian for a one-dimensional system, and it simply has 4 terms in it, which are the 4 ingredients that I showed to you in the previous slide. So here is the dispersion relation of a free particle in a parabolic band with a chemical potential here, an important one. These tau operators are responsible for particle-hole symmetry. So this is a nice trick from superconductivity to define these tau operators. They look like Pauli matrices if you look at them, but they just tell you that there is a copy of the system with all the energies negative for particle and hole. So there are all these taus everywhere. Now this is which term? Spin orbit term, that's right. So you have momentum and spin here. This is Zeeman term, spin and magnetic field. And this is superconductivity, described by delta and with a particle hole tau in the front. So put these 4 terms together and you get Majoranas. This is actually a very simple single particle calculation, no interactions, and so on. So once again, conceptually what happens is the following. You start with this kind of a fully gapped spectrum. That means you have a superconducting one-dimensional system with gaps around Fermi level. And now I'm showing particle and the whole part of the spectrum. There's always this complex conjugate particle-whole part. So this is for small magnetic fields. At this critical point where you have Ez equal to delta, you have this middle gap closed. And by the way, this spectrum here is exactly linear. So you have a little Dirac cone in there. And this is the reason why you have Berry phase cancellation. For those who know what this means, in Dirac systems like graphene, you have a Berry phase of pi going around the Dirac cone. And so this is where you get it from in this one-dimensional system. Now you keep increasing magnetic field. Gap is recovered. Gap is back. But you cannot see it from the spectrum, but the gap is actually negative. The gap is opposite sign. And you have entered this topological superconductor with a negative gap. So this is, in fact, a phase transition. So if you had this one-dimensional system and you had some superconductivity in it, some spin-orbit interaction, and you start ramping up the magnetic field, up and up and up and up and up, you will go through a phase transition from a trivial state, which is a one-dimensional S-wave superconductor. You will go into the topological state as a function of, in this case, magnetic field. You can also do it as a function of other things. For example, as a function of the chemical potential in the system. You can just sweep the chemical potential and go. When you enter this gap, you will go into the topological state. You can also do this transition as a function of position. So imagine this invisible tube here is a one-dimensional system, and I somehow create conditions where to the left here you have this condition where magnetic field is smaller than the gap, and to the right there you have a different field and it's exceeding the gap in this system. Then right here in the middle there will be one point in the entire infinity where Ez is equal to delta. And at this point, at this one point, due to this Dirac cone spectrum, there will be a stable level at E equals 0, and it will contain a Majorana fermion. Now, the second one in my theoretical example will be at infinity. The second Majorana will be at infinity. But if I have a finite size nanowire like this where I'm creating this, then there could be an edge here and the second edge here, where I go from a topological region to a trivial region. So inside a vacuum, gap is positive. So what is the difference between topological superconductor, the spinless p-wave system, and trivial superconductor? From our point of view, the difference that you can measure, you can see, is just whether or not these Majorana fermions are there at the edges of the system or not. So this is a spectrum, energy versus position. Boundaries of the system are here and here. And at zero energy, you have these extra states that would not be there in a trivial case. So how does the phase transition occur? You start closing this gap by some means, magnetic field or temperature or chemical potential. At some point, the gap is closed. What happens at this point is, like around any phase transition, the coherence length grows and grows and grows and reaches infinity. So in a superconducting phase transition, coherence length becomes larger and larger, closer to the critical temperature, for example. So in this case, Majoranas grow and they grow until they meet each other. And this point where they met each other, it becomes a trivial system because these two unpaired Majoranas form one fermion. And so now you just have an extra fermion in your nanowire. Nothing interesting. And this fermion lives above or below the gap or in some coupled state, in some Bogoliubov quasi-particle state, which is a superposition of electron and hole, but it is not an equal superposition of an electron and hole. And therefore, it is not a Majorana fermion. It is a Bogoliubov quasi-particle. So then you can go again through the phase transition, and Majorana fermions can be localized at the edges of the system. Okay. So, great. These kind of ingredients that we talked about, a semiconductor, a superconductor, magnetic field, spin-orbit interaction, this is all reasonably available in the lab. You can actually, we had it in our lab at that time when these proposals came, so we got very excited about this. But the question remains, how do you measure? How do you detect that there is a Majorana fermion? So actually, if you think about it, it's not so easy. So they're spinless, right? We'll remove the spin degeneracy. So they're spinless, so you cannot do a magnetic measurement. They're chargeless. They don't have a charge, right? Because they are equal superposition of electron and hole. They're massless because they are in a Dirac cone where mass is zero. Like a mass of a photon is zero, right? They're massless. So not so easy to measure them. So the way to measure them is to actually tunnel into one of them and then tunnel into the superconductor. So by a process known as Andreev reflection. Andreev reflection is a manifestation of this particle-hole symmetry that we already talked about. And it's a way to pass a current between a normal conductor, normal contact, meaning a metal, not a superconductor, and a superconductor. The way this goes is, let's say an electron comes in, an electron sees this gap. What is the meaning of this gap for an electron? It means there cannot be any electrons inside the gap. Electrons can only live above the gap. And inside the gap, only Cooper pairs are allowed. So paired states, the bosons, the paired electron states. So how can we construct a process in which we get current into the superconductor? Well, a Cooper pair must go this way, but now we started with one electron, and now we have two electrons that continue traveling. So there is a charge conservation problem. How do we solve it? We send a hole in the opposite direction. So this way, electrons go there, hole comes back, and therefore current that goes this way is 2e, right? Plus charge going this way is like minus charge going this way. And so there is a continuity here, current just 2e going all the way through. So this is called Andreev reflection, meaning electron comes in, hole goes back. That's Andreev reflection. And Andreev reflection allows you to have a little bit of current inside the gap. So this is the gap, and this is some voltage here. So voltage means you can, adjusting the voltage difference between the normal metal and the superconductor, you can give these particles some energy, some chemical potential difference. Until you exceed the gap, there should be no current. But due to these Andreev processes, there is a little bit of current going here. And then if you just apply a voltage that exceeds this gap, so a gap can be, for example, a milli-electron volt. So if you apply a millivolt to this system, then you are free to tunnel, because above the gap there are single particle states available for you. So you can just tunnel and you get this current. Actually, you get this sharp peak in current. This is a well-known phenomenon from the BCS theory of superconductivity, that the density of states is very high at this boundary here. It gives you this anomaly. They're called quasi-particle peaks. So this is a way we are going to do the measurement. Now, what happens if we now add a Majorana level to this system? This is what happens. Here is the energy spectrum with the Majorana in it. So you have a level exactly at zero energy, close to the edge of the superconductor. And you are going to tunnel into that level with an Andreev process. So you need to come in with an electron at this energy, which is zero, which means zero bias, no voltage between normal and superconducting. And you're going to get a hole going back at the same energy, at zero bias. And what the theory shows you is that you are going to have a huge increase in conductance. In fact, theoretically, it should be quantized by 2e squared over h. A peak in conductance exactly at zero voltage where you have the Majorana level. So whereas before you had nothing or a very small current there, if you have Majoranas, if you enter the topological state, if you went through the phase transition, there is prediction of a huge peak. Why is there a huge peak? It's because there is a resonance tunneling process. It is actually analogous to a resonance tunneling that you might have encountered in quantum mechanics. So for example, you have a double barrier system like this, and in between the two barriers you have some quantized levels. If the barrier heights are different, and you're trying to tunnel from here to here and out, you're going to have some resonance where the level is, because transition probability will be strongly enhanced by the level. But it will not be something quantized. But if the barriers are exactly the same height, so if the barriers are exactly the same height, you have this resonance. So when tunneling through here is exactly symmetric to tunneling out, tunneling in and tunneling out are exactly the same, then you have a huge enhancement of the tunneling probability. So you can just work it out from WKB, from quantum mechanics, that this is the case. You have optimal tunneling conditions when the two barriers are the same height. And so you get a peak that is exactly maximum quantized in this case. Now, why does this apply here? Well, it is because when you tunnel in with an electron and go back with a hole, it is kind of like going and tunneling through the same barrier twice. So this will be the electron process, this will be the hole process, but the barrier is the same barrier both times. It's the same one single barrier. You're just going in and out. And so you have exactly the resonance tunneling situation for this Andreev process at zero bias. At any other bias, it's not the case because for different biases, the barrier may look different. Okay? So it's a resonance tunneling process leads to this conductance peak, enhanced transmission of particles. So we use a Majorana level as a box which we occupy and deoccupy with real electrons, or holes. And by this way, we discover that it's there. We discover its existence. Okay. So now about experiments. We're going to see a couple of experiments today, one with semiconductors and one that came a couple of years later with magnetic atoms. But they both map Kitaev Hamiltonian onto these four ingredients. So for the nanowires, the system looks like this. Here is a nanowire. It is a couple microns long. And it is made of a semiconductor called indium antimonide. Why this choice? For a couple of reasons. First of all, it has a strong spin-orbit interaction. Second of all, it has a huge G factor. G factor is this thing in the Zeeman term, right? Zeeman energy is G mu B, and G factor is this prefactor here. And in a semiconductor, it can be not equal to 2. Like for free electrons, it can be something else. And for indium antimonide, it is equal to 50. And it's the largest of all semiconductors in this family of materials like gallium arsenide, indium arsenide, indium antimonide. This one is the largest. It is also convenient from experimental point of view for different reasons. It's clean. It's a single crystal, this one-dimensional single crystal with no defects in it. It is also very amicable to metallic contacts, like as shown here. So this is a basic, simplest device you can build with this nanowire. You lay it down and you put 2 contacts on it. And this way you can pass an electrical current through. You hook it up to a battery and to an ammeter, and you apply voltage, measure current. And these are the kind of experiments we're going to be looking at today. These are called transport measurements, but they are also going to be tunneling measurements. So meaning there's going to be a barrier somewhere here. Okay, so how do we know it's a one-dimensional wire? We can actually observe one-dimensional transmission through this wire. So these dashed lines mark conductance quantized in units of e squared over h. So this one is 1 squared over h, 2 squared over h, 3 squared over h. And when you have resonances that line up with these, this is data is a couple years old. Now there are more of these plateaus and they're more clear in the latest data. But when you have such plateaus, you can count the number of one-dimensional modes occupied in this nanowire. And so here you can see 3. And that means that if you look at the nanowire in a cross-section, this is going along the nanowire. This is a confined system for electronic waves. Electrons are like waves in a waveguide, like photons in a fiber, and they travel through this waveguide unperturbed, like wave packets in a fiber. And so if you have 3 there, that means there will be one like this, another one like this, and a third one like this, like quantized modes in a particle in a box potential. And each one will give you a conductance of 2 squared over h. So this is a basic result from quantum transport. It was discovered 25 years ago. and you can see it in these nanowires. So they're one-dimensional quantum wires. Now, the spin-orbit interaction was measured in these nanowires a couple different ways. I'm not going to show you here, but it was extracted to be something like 50 microvolts strong. So what does it mean? The two one-dimensional parabolas split, and if you measure this distance, this is this ESO, was measured to be about 50 microelectron volts. It's 50. And since then, this estimate was revised upwards by about a factor of 10 to 20. So it is actually a pretty large energy scale. Why do I say it's large? Because we can compare it to some other energy scales. So for example, we can convert 50 microvolts into temperature. That's 1 Kelvin. So if you do an experiment at 10 or even 100 millikelvin, you are way below this energy scale. If you plug in 500 microvolts here, that's going to give you almost 10 Kelvin. And so 10 Kelvin for these kind of experiments is a very high temperature. Because we work at 10 to 100 millikelvin in these experiments. You can also convert this into a spin-orbit length. Spin-orbit length is a length, if you start with the spin up, then how long it will take for a spin-orbit interaction to flip spin down as it travels along the wire. So it gives you a length scale on which spin-orbit interaction acts. And so this length scale is 200 nanometers. If you plug in a larger number, it will shrink more and more. It can become 100 or 50 nanometers or 10 nanometers. And then you compare this to the length of the nanowire. So the length of the nanowire is a couple microns. And this is at least a factor of 10 smaller than the nanowire length. So this is a good spin-orbit strength, a good ingredient for our Majorana recipe. Then the third ingredient is superconductivity. How do you verify this? Well, in a simple device like I already showed you, here is a nanowire, and here is a superconductor. You put two superconductors on a nanowire, and you pass a current through it. You observe current flows without resistance, meaning that you have supercurrent. Supercurrent looks like this. You ramp up the current, and you follow the red trace. There is no voltage developing here. And that means current flowing without resistance is due to superconductivity, meaning you have induced superconductivity in this nanowire. And this is the kind of superconductivity that people work with in experiments. It's the induced one. So superconductivity is provided externally by this metal that lives on top of the wire. And the nanowire becomes superconducting by proximity, meaning that Cooper pairs from the superconductor travel into the semiconductor and remember their superconducting correlation for some time or for some distance. And close to the superconducting contact, there is a region in a semiconductor which is proximatized superconducting. So superconducting by proximity to a bulk superconductor. And we are going to be creating a topological phase in this proximatized region. So now this is a full device where experiments were done. It has already many ingredients that you can recognize. Here is a nanowire. Here is a superconductor lying on top of the nanowire. This contact here is a probe. So this is the normal metal from which we're going to launch our Andreev tunneling into the superconductor to check if there are Majorana fermions there or not. Now, all these lines underneath are metallic gate electrodes. They're separate from the nanowire by a layer of dielectric. So this is a boundary of the dielectric. And these are all gates. What do these gates do? they allow us to shape the chemical potential in the nanowire, change it locally. For example, one of the narrow gates here we can use to create a barrier between the normal and the superconducting regions, and then we can tunnel through that barrier. How do we create a barrier? We make a negative voltage on this one little gate, which depletes the electrons in the nanowire. So it repels them from that region, reduces the density until it's zero, and you have created a tunneling barrier. These wider gates also play a role. They change the chemical potentials, mu left, mu central, mu right. Chemical potentials in this topological region can be control knobs for going in and out of the topological phase. And so these gates are very nice to have. You can see there are many gates to tune this device overall. Now, we expect Majoranas to appear here at the boundaries. In this experiment, we are only looking at this one at the top, but we could also, and we are doing this, make another probe here, or normal or superconducting, and look at the second Majorana at the bottom. So some of the newer experiments include a probe here to look at the pair simultaneously. And what we are after is this zero bias conductance peak. And indeed, I wouldn't be giving this lecture for you if this didn't occur. Zero bias conductance peaks were observed in these devices. Sort of the most commonly used data set is this one. What does it have? Let's start at zero magnetic field, which is the lowest trace here, and then the traces go up by 10 millitesla until they reach about half a Tesla. And they are offset for clarity so that you can see what's going on here. The lowest trace does something like this. It has a feature with two ears and a suppression around zero bias. So there's no zero bias feature, but there is this suppression, and there are these ears at the positions about 200 microvolts. So these ears are what we recognize instantly as being the superconducting gap induced in the nanowire. So because there is a superconductor close to the nanowire, there is a reduced number of electrons inside the gap. They are all coupled into Cooper pairs. They want to be paired. And they pile up, all these states that are not here, they pile up at the edges of the gap. And outside the gap, we have a higher conductance than inside the gap. So this just shows us that we have induced superconductivity in the gap. Now remember, this is a one-dimensional nanowire that we're tunneling into. It has spin-orbit interaction, and we have induced superconductivity. So there's the three ingredients. The fourth ingredient is magnetic field, right? So this is what is shown here. And we increase magnetic field, and at about 100 millitesla, around here, we start seeing this little feature emerging. And then it develops into a zero bias peak, which sticks to zero bias, does not move away for some considerable range of field. And so this feature was studied from different directions to check whether it conforms to Majorana Fermion hypothesis. It seems to be holding so far. Of course, experimentally, you can always ask questions and dig deeper into these things, and that's what we're doing in my lab at Pitt, among other things, studying this feature and trying to find more signatures of that this belongs to Majorana Fermions. But already a few years ago, there was quite some evidence mounted that this is the case. So, for example, the fact that it sticks to zero bias is very significant. Remember, I told you that these Majorana states are edge bound states of a topological phase. And they are pinned to zero bias by this particle hole symmetry and by being on the transition between trivial and topological regions. So they somehow are not allowed to move away from zero bias because they are the bound states on the edges of a distinct topological phase. And that's what this peak does. So for comparison, if this zero bias peak had some spin, then in indium antimonide, it would move with a slope like this. as we increase magnetic field, this feature would shift very rapidly out of the gap if it had spin. So this is not a state that has spin, or it has a very small G factor, not like an electron in indium antimonide. Now, why is it such a tiny peak? I told you that conductance should be quantized in the units of 2e squared over h. So it should reach right here. And in this simulation, you have the light gray lines, which show you a calculation in a pure system and done at 0 temperature. And the difference between the light gray, which I will now highlight for you. Light gray does this. Now it became bright red. The difference between bright red and black here is temperature. So red is 0 temperature, and it's an ultra sharp peak, which goes to 2e squared over h. Black is finite temperature. We were at very low temperature in our measurement, but we were at finite temperature. We were at about 60 millikelvin. And so the area of the black peak is the same as the area of the red peak, but it is broadened by temperature, and it shrinks. So this seems to explain very well what is going on with the height of the peak. And one way to check it is to check it for different temperatures. So this is going from 60 millikelvin to about 400 millikelvin. And this is, I apologize, the axis didn't work out, but this is about 0 to minus 100 microvolts. And this is for different temperatures. This is a conductance scale, and the height of this peak here is 0.05 of e squared over h. So this gives you the vertical scale, the horizontal scale of these traces. But what you can see here is as we ramp up the temperature, peak broadens and merges into this background until it's completely gone. And by the way, it is gone at a temperature which is of order 1 Kelvin, which was the spin orbit scale that I told you. Right? So of order 1 Kelvin was a spin orbit scale, and the peak seems to be gone by then, so it's kind of consistent. Okay, I want to show you one more check that we did among many back then, and that was a very interesting check to check whether spin orbit interaction was a relevant ingredient in the appearance of this peak. Right? So what you can do is you can take out spin orbit interaction and see if peak disappears. If peak disappears, that means the spin orbit interaction is important for its creation, and spin orbit is a cornerstone ingredient in this list of 4. Now, you can't really take out spin orbit interaction. You cannot just say, okay, this material, you no longer have spin orbit interaction. This is not possible, but something else is possible. Spin orbit interaction in a 1D system can be thought of conceptually as a magnetic field. So it's a magnetic field that acts on moving electrons, and it's proportional to k, the momentum, and spin, and it is pointing in a certain direction. And we've measured it in different experiments to be pointing perpendicular to the wire. So nanowire is this way, field perpendicular to the wire. And then what happens if you line up your external field with a spin orbit field, you basically make this field ineffective. These are the two relevant situations for this case. So when external field is perpendicular to spin orbit field, then the spin orbit split spectrum develops a gap here, which is very important in the creation of Majorana Fermions. I did not explain it to you because I started from superconductivity, but if you didn't have superconductivity, in this situation you would have this gap, and this gap is important for lifting spin degeneracy because you have only 2 modes, spin up going this way and spin down going this way in a system. So this is a spinless helical liquid system. So without this gap, there are no Majoranas, because without this gap, you have 4 bands crossing Fermi level, and the 2 2 and 2 make 2 Majoranas, and they make a single fermion, and there is nothing interesting. So this is actually the case when external field is aligned with spin orbit field. Spectrum looks like this. Basically, 2 fields are acting in the same direction, and they act like one field. You don't have 2 fields to couple these spin up and spin down here and open a little gap and lift spin degeneracy. You just have 2 spins shifted by a Zeeman energy here. So experimentally what that means is that if you align the 2 fields, zero bias peak should disappear. And this is what was observed. Now this is in a data in color scale. This is the scale of the gap, 2 delta. And the color here is conductance. Red means high conductance, blue means low conductance, and white is in between. So starting at some magnetic field, you start seeing the zero bias feature developing. And that's the Majorana situation, because in this case, we have the 2 fields perpendicular. So this is a zero bias peak coming up in magnetic field inside the gap, which is blue, inside the suppression. And now this is what happens when the 2 fields are aligned. B parallel to BSO. There is no feature inside the gap. This was done for many different angles to map out when it appears, when it disappears, to check that spin-orbit interaction is an important ingredient in the creation of this Majorana recipe. So this is one of the checks that was done. Okay. In the remaining 10 minutes, I want to show you one other experiment that occurred in the meantime. This was 2012. There were many, many experimental and theoretical works. The total field is over 1,000 papers, most of them theory, but also several very interesting experiments. I'm just going to show you one, and it is a little different, but conceptually the same. So the system is a perfectly smooth atomic superconductor surface. This is lead. And on top of that, a chain of atoms that have spins. So magnetic atoms on top of lead. Now, how does this create a Kitaev Hamiltonian? How does it map onto that? Very similar way. But the ingredients are a little shuffled. So the first ingredient was 1D, one-dimensional system. That's just having one-dimensional chain gives you that. Each of these atoms contributes 1 electron to the band structure, so you have a 1D right there. The second one was spin orbit. Spin orbit, in this case, comes from the superconductor. So these atoms don't have spin orbit, but this lead has a very strong spin orbit interaction, and it is donated, just like superconductivity, to the magnetic chain. The same for superconductivity. It comes from lead. The fourth ingredient was magnetism. Magnetism is due to the ferromagnetic arrangement of these atoms. So they have discovered that when they put a chain together, all the spins are pointing in the same direction. And so you have all the same 4 ingredients in this system. So maybe you're going to have a Majorana fermion here and a Majorana fermion here. Right? And what would be the measurement? The same. Looking for a zero bias tunneling conductance feature, but in this case with an STM tip. So they have a scanning tunneling microscope with an atomically sharp tip. They can move it around, which is nice because they can get a spatial map of this chain and see where the peak is and where it isn't. They can bring the tip close to the chain, and then they can tunnel from the tip into any atom on this chain and look at the spectrum. See the gap, see something inside the gap, maybe a zero bias peak, and so on. So it's this paper from The year doesn't appear, but I think it's last year. And it's from a Princeton group. And of course, they also have done extensive calculations, both analytical and also numerical, to verify that this is highly plausible that Majorana fermions could be expected in this system. Because it's not just about having all these ingredients, but they have to be in the right proportion, of course, to give a topological phase. Okay, so this is their technique. They have a superconductor, and they prepare inside an ultra-high vacuum at low temperature very smooth surfaces of this film by cleaning it with an annealing and a beam of ions that cleans it off. So this is a 110 surface of lead with a lattice constant of about 5 angstroms. And these colors here are atomic terraces. So the difference between beige and brown is a single atom height. And so they have this huge area, many, many atoms of exactly the same lattice plane. And they go to low temperature, below the superconducting transition of lead, and they observe in their tunneling experiment, so from a tungsten tip into lead by tunneling through vacuum, they observe this superconducting spectrum with a very nice gap. So nothing inside the gap, no conductance, no tunneling allowed inside the gap, and sharp features at the edges of the gap and high conductance outside the gap. So just like I described to you in a nanowire, except in a nanowire experiment, the probe was the nanowire itself, and the barrier was made by a gate. Here, the barrier is vacuum. The probe is an external metal tip that can be moved around. Okay, so this is a superconductor. They have a nice and understandable superconductor with a basic superconducting theory. Now for nanowires, what they do, it's very nice. They put these iron atoms, they sputter a little bit of them on this metallic surface of lead. So these are, again, the atomic terraces of lead in color here, and these bright blobs are the iron atoms. And by playing with conditions for how they put them down, by changing temperature and the rate, they observed that they mostly form these kind of clusters. So iron atoms want to be together in clusters. But sometimes what happens is out of one of these clusters, a one-dimensional chain of atoms grows. And this is exactly what they need to do their measurement. Right? This kind of one-dimensional chain of iron atoms. So they found a bunch of them. There is always a cluster in the middle. And the scale here, you can see it, angstroms. So in the last experiment, we had microns with nanowires. This is angstroms. This is in the scale of single atoms. And out of one cluster, they can grow a chain left and right, or maybe in one direction. And they found quite a few of these. Next thing they did was they verified that these chains are magnetic. Right? Magnetism is an important ingredient. They saw superconductivity, now magnetism. How they did that? They used a spin-polarized STM tip. So what they did was they took their tip and they dipped it in a magnetic material, and then they got some spins on the tip. So now your tip has some magnetic material on it, and with that magnetic material, you are probing a chain of spins. Then you are using this magnetoresistance effect, where under the influence of an external field, a chain might flip at a different time than the tip. And then for parallel alignment of chain and tip, you have higher tunneling current. And when they're aligned in opposite directions, you have a reduced tunneling current. And then in the tunneling experiment, you have this hysteresis. So this is a spin valve type of measurement, if you know what this means. This is kind of like a spin valve, atomic spin valve, and they have a little bit more contrast here than they have here because the tip and the sample switch at different times. So finally, here is their data. I already showed you color plots in this talk. So color means current, tunneling current in this case. But this is a spatial map. And these blobs are sort of a few atoms large. So this is a scale of 100 angstroms here. So it's a few atoms in each blob. This is the chain. And these different cuts, these different slices are for different bias voltages between the tip and the substrate. So different energy difference between the probe and the chain. So here at the far extremities of this plot, they are outside of the gap. And when they're outside of the gap, they have a large current going in to the chain. And here in the middle, they go inside the gap. And current goes down. But the most interesting measurement is here at zero bias. So at zero bias, with their spatial resolution, where they can scan the tip along the chain, they see that there is a larger conductance, and it's larger at the end of the chain. So where you expect the Majorana, they have a highly localized large conductance region, and they have stated that this they consider to be a signature of Majorana Fermions. So this is maybe the most remarkable experiment that happened in the past 3 years since the initial nanowire work, and very nice for you guys because there are many similarities between the two measurements. Slightly different combination of ingredients, very different physical realizations, atomic level or semiconductor, superconductor, but conceptually very similar. And now, as a function of space, you can see some kind of feature localized here. Does this serve as a smoking gun, ultimate proof of Majorana Fermions? Perhaps not. Experiments will continue, but in any case, this is what we have for now, and this is what I wanted to tell you today. Thank you for your attention.